In the previous video we discussed the state-of-the-art single-junction thin-film solar cells. Let's move to the thin-film silicon solar cells based on double junctions, or in other words, the tandem cell. The tandem cell of interest is the earlier discussed amorphous nanocrystalline silicon tandem cell, or also referred to as the micromorph tandem cell. In the video on the stable Wronski effect, we already stressed the fact that 2/3 of the power depends on the amorphous silicon top cell in a micromorph tandem cell. This cell suffers from light-induced metastability. Achieving record efficiency means that reduction of the effect of stable Wronski effect in the top cell is crucial. The record micromorph cell has been processed by researchers at EPFL Neuchâtel in Switzerland. They obtained the record efficiency by using a superstrate PIN-PIN cell configuration. As front electrode, a textured boron doped zinc oxide deposited on glass was used. Then the amorphous silicon PIN junction was deposited. The important innovation is that a 70 to 150 nanometer thick N-type silicon oxide layer was deposited with a low refractive index, namely 1.75 at a wavelength of around 800 nanometers. On top of this intermediate refractive layer, a conventional N-type nanocrystalline silicon oxide layer was deposited, followed by the nanocrystalline silicon bottom cell and the back contact. The high refractive index contrast between the top cell and the intermediate refractive layer allows high back reflection into the top cell. As a consequence, both high absorption and high current densities are in the top cell achieved. Therefore, the thickness of the top cell can be made thinner. The beneficial effect is that the light-induced degradation is reduced, as the recombination at these metastable defects is a bulk process. By further optimizing top cell and the intermediate refractive layer, the researchers at EPFL achieved a record stabilized efficiency of 12.63%. Another concept for micromorph tandem cell was discussed in the video lecture on surface roughness. We discussed the integration of modulated surface texturing in the glass substrate, the TCO surface and the amorphous silicon surface as developed at the Delft University of Technology. This approach resulted in a good light management in combination with the growth of high-quality nanocrystalline silicon, without defect-rich filaments. In addition, in the device shown here, a double layer of hydrogenated indium oxide and intrinsic zinc oxide as front window layer has been introduced. This front electrode has superior conductivity combined with high transmission. This resulted in a record initial conversion efficiency of 14.8% for micromorph tandem cells. Stabilized efficiency was slightly lower than the record device of EPFL. This device concept, however, has still room to improve the stabilized efficiency further. Let's scale up. We make the step from lab device to real modules. A typical module has a size of 14,300 squared centimeters, which is 4 orders of magnitude larger than the size of the lab-scale devices discussed in the previous slide. This equals the generation 4 size in the display industry. We have discussed the module manufacturing in an earlier video. Here you see a typical module processed using equipment of Tokyo Electron based on the micromorph tandem cell concept. The record module conversion efficiency obtained by Tokyo Electron is 12.34%. This is an impressive achievement as you consider that 12.63% is the record for a device area of only 1 square centimeter. Upscaling the micromorph technology from 1 square centimeter up to 14,300 square centimeter, only 0.29% in efficiency is lost. This shows that thin film silicon processing is a highly mature processing technology. An advantage of thin film PV technology is that it has the potential to be integrated into a flexible module product. We have discussed the innovative manufacturing process of thin film silicon flexible modules at Hyatt Solar. Here you see an example of their lightweight flexible module based on micromorph architecture. One of the advantages of silicon in general is that it is quite resistant against water. This means that it does not require expensive encapsulation materials with extreme water barriers to encapsulate thin film PV. This allows to make a relatively cheap, lightweight, flexible products as you see here. The production is currently mainly focused on the single junction amorphous silicon technology. However, they also have demonstrated a flexible micromorph product with a conversion efficiency of 10.9%. The next generation micromorph flexible product is expected to have a module efficiency above 12%. Now, let's add one subcell and move to triple junctions. The record conversion efficiency for thin film silicon PV technology has been obtained using the triple junction device architecture. The record was established by researchers at AST using the substrate NiP structure based on amorphous silicon top cell and a nanocrystalline silicon based middle and bottom cell. As discussed in the lecture on light-induced degradation, 50% of the power is produced in the top amorphous silicon cell. This cell might partly suffer from light-induced degradation. Researchers have combined two innovations we discussed earlier. Again, the innovative honeycomb structured back reflector was used as substrate to facilitate good light trapping and the growth of high-quality nanocrystalline silicon. This is similar like for the single junction nanocrystalline silicon NiP solar cell with the record efficiency. The additional innovation is the integration of dense, high-quality intrinsic amorphous silicon in the top cell using the triode PECVD technology. This innovation resulted in the record stable conversion efficiency for amorphous single-junction solar cells. Furthermore, the effect of the current mismatch in this triple junction architecture was smartly utilized. In the video lecture on the current matching, we discussed that the fill factor of multi-junctions that are current mismatch will be higher than for multi-junctions that are nicely current matched. In spite of the higher values for the open circuit voltage, the amorphous silicon solar cells have the lower fill factors than the nanocrystalline silicon single junction solar cells. As you can see in the EQE of this triple junction cell, the top cell generates by far the highest current. This means that the fill factor is not limited by the amorphous silicon junction with the poorest individual fill factor. As a result, a relatively large value for the fill factor is obtained for the triple junction solar cell. The stabilized efficiency of 14.0% is currently the record conversion efficiency for thin film silicon devices. Interestingly, the combination of high-quality amorphous silicon and the current mismatch results in an extreme small difference between the initial and stable conversion efficiency. This relatively difference is only 4%. We will continue our discussion of the state-of-the-art thin film silicon multi-junction devices in the next video.